recent experiment I have been doing in my NARS system by using the existing reasoning and learning mechanism to process natural language, which is, of course, just at the very beginning, so I don't have the full solution for NLP, but I hope you will find this approach interesting and novel in a certain sense. The basic idea is, once again, like I treat many other things, I'm after a unified approach, meaning that there is no separate NLP module in NARS. Instead, I'm going to represent linguistic knowledge in the same way as the other form of knowledge, and also use the learning mechanism to learn linguistic knowledge from the system's experience, and use inference rules to control the learning process, or to carry out the learning process. And also, finally, to treat language understanding and production as reasoning. These are, of course, all big topics, so given the limited time, I will have to run through NARS very fast, okay? And then talk about how to do natural language in that framework. First, knowledge representation. You see, everything starts is represented in the simplest form as a term. A term is a name of an internal data structure, or you can call it a concept. Once again, in this sense, it's very different from the traditional symbol. So it doesn't denote object in the world. Okay, it's the same idea as proposed by Professor Shapiro yesterday. Also, a term not only can correspond to a word or a concept, it also can correspond to a sensation, an action, or something else. So actually, in this approach, I don't really make the traditional distinction between symbolic and sub-symbolic level. It's a matter of degree. Okay, the distinction is still there, but there is no sharp boundary. And also, finally, a term may be a compound. It doesn't have to be simple. It can be a structure formed by other terms in various ways. And then when two terms link together by something called a copular in linguistics and logic, then it will form what I call a statement, which actually indicate to what extent these two terms can substitute each other or can be used as each other. So that's the very basic idea of this formal language, which is fundamentally different from fourth-order predicate calculus in several ways, which I cannot explain now. So roughly speaking, now in that sense, you can see the memory of the system is some kind of network. With the terms as the nodes, with the statements as the links. You see that some of the terms are just internal IDs, and some others may correspond to words in different language, and some of them may even represent image or actions which I cannot draw. But that's the idea. And here I only indicate two types of links. The blue ones are what I call inheritance. It's kind of like forms similar to a SR hierarchy. And then the green ones are the represent relation, which, since we are talking about natural language processing, and that's of special interest. So you can use a word to represent a concept or something like that. And then one thing that makes this kind of reasoning system very different from traditional reasoning system, I think the number one issue is actually in semantics. It's not that much in the rules or language. Here, I actually redefine what is truth and what is meaning compared to the conventional usage. In this system, true is a matter of degree, but this matter of degree doesn't measure how much a sentence match a reality in a model or in the world. Instead, it measures evidential support. That is, according to the system's experience, how much of the evidence support this statement or claim. Then technically, I'm using two numbers between 0 and 1 to represent this degree. The first number is what I call frequency. The second number is what I call confidence. Frequency is the proportion of positive evidence among all evidence. So intuitively speaking, it's similar to probability, even though it doesn't take a limit of this ratio, or it doesn't even assume there is a limit of this ratio. Then the confidence value is the proportion of currently available evidence compared to the evidence you are going to have after the coming of a new piece of evidence of a certain amount. Okay? So you compare what you have with what you are going to have. So this one is more novel than the other. Intuitively speaking, confidence 0 means I don't know, I have no idea. Then as far as when I'm getting more and more evidence, confidence is going to grow to be higher and higher, but you see it never reach 1. So the system is never absolutely certain about anything. Or in other words, there is no absolute truth in this model. That's why it's called non-axiomatic logic. Okay. Another thing is the meaning of a term. Again, it's not a denotation. Also, it's not determined by a definition. Instead, it's determined by what the system knows about it. So clearly, when the system is getting more evidence or more experience, the meaning of related term may change over time. So it's not a fixed thing. Then there are a whole bunch of inference rules. Each of them take typically two premises. Each of them is represented in the link I mentioned before. And depend on their different combination, there are different type of inference, which include a whole bunch of different type. Also, each inference rule has a truth value function, which will calculate the truth value according to the truth value of the premise. Calculate the truth value of the conclusion according to the truth value of the premise plus the type of the inference. Okay? And they are not built according to probability theory, but according to something else. Then the most important philosophical assumption I made in this system, which I have mentioned before in the workshops, is that intelligence means to be able to work with insufficient knowledge and resource. Concretely speaking, it means the system only have finite information processing capacity, but it has to work in real time and to be open to unanticipated tasks. Okay. As a result, when processing a task, like when answering a question, the system cannot, in normal situation, take all knowledge into consideration, just because of time restriction. For the same reason, when the system is using a concept or a term, typically it doesn't use all of its meanings. Here, meaning, it means the relations with the other terms, which also explains why meaning change in different contexts. Also, another result is the system is an adaptive system. It continuously changes its internal state. It will never repeat its previous state in its life cycle. That's another thing I mentioned in the workshop. As a result, at the problem-solving level or at the task processing level, it cannot be seen as a Turing machine anymore because there is no unique initial state with respect to a given task. Even you repeat the same problem, since the system receive it at a different state, the processing may be the same, may be different. It's not guaranteed, which is what I call a case-by-case problem solving. So the problem, how the problem is solved, depends on the current moment, what knowledge the system has, how much it can be taken into consideration, whether there are competing tasks, and so on. All those things change from moment to moment. So that's kind of like a very rough top-level description. So you get the input, and which put into a buffer, and some of them are selectively put into the memory, which is some kind of network. In each working cycle, typically toolings on one node is selected as a premise and feed into the inference engine, which will decide which rule to be fired, which will produce a bunch of conclusions which go back to the buffer. And some of them will be selectively reported to the user, and the system just keep doing this in its life. So how to apply that into natural language? Well, that's a very simple example. Again, that we start by giving the system some input, the first 3 lines. Okay. Here, roughly speaking, it means here all the bold terms are the English words. Okay. This kind of normal terms are the internal concepts. I'm using English again just to make understanding easier. So this basically means the cat word represents the cat concept within the system to a certain degree. Here I'm using, for the input, I'm just using the default truth value, which means, I tell you this is the case and you should believe it to a certain level or to the normal level, which is what this 0.9 as system parameter is indicating. So you'll see that, again, for the same thing, fish is represented by the fish concept. And this is a very simple sentence so that you can say, cat eats fish. Then within the system, it basically say that the cat concept and the fish concept has a relation which is the former can take the later as food, something like that. Okay? And so this sentence represents this internal relationship. Okay. So you'll see the big picture is, once again, the system is trying to build up some kind of correspondence between components in a natural language like sentence, phrase, or words on one hand, and on the other hand, the internal representation, which can be a simple term or compound term, okay, which is like what the RPI team has reported previous day. But here the difference is the internal representation is not first order predicate calculus, and also the mapping is not a one-to-one mapping. It's actually a many-to-many mapping. Also each relation, each map have a strength indicated by this truth value. Then the system begin to do, well, I will skip all the other things just to see the basic step. So, for example, if the system take this one, and the induction rule, in one version of it, will be applied to produce something like this, okay? Which is not very easy to read, but basically these are variables. Okay. What's going on here is actually this version of induction is very similar to the anti-unification in the HDTP model, which will be reported again right after this talk. So it's a generalization. Say that if this thing applies, this kind of mapping can be used between those two concrete situations. Maybe if I replace some one of the components by a variable, or later used by another constant, maybe the relation is still true. Okay, so you can see this is basically saying that if something represents, well, if some word represents some concept, okay, if that word is put before eat fish, and then that basically means that kind of thing can take fish as food, something like that. Okay. So, or in other words, we can say this conclusion represents what the system learned about the phrase eat fish, according to the given example. One thing I want to pay attention is the truth value of this is actually relatively lower. The confidence level is relatively lower because induction, in a sense, only produce a hypothesis. In this system, it will never directly draw a strong conclusion from a single case. But if this kind of situation, this kind of phrase happen again and again and again, it's always get confirmed. As you can guess, the confidence level of this conclusion will increase. Okay. Then, using the same approach, if you do induction again for the other pair, you'll see you get an even more general pattern. So this time is about eat. Okay, so this will be the system's knowledge about what something something else means, according to the given evidence. And this one, since it's kind of like double induction, you see the confidence level is even lower. Okay. And then you see that if I further provide the system additional knowledge about individual new words about, say, dog and meat, then combining them with the kind of the pattern produced before, using deduction, the system can begin to guess the meaning of new sentence, which it never ran into before. Like, for example, we guess probably dog eat fish means and dog and fish have the food relation to a certain degree. Okay. Similarly, this one contains actually two new words, and dog eat meat probably means dog and meat have this relation. So you can see this as natural language processing. You can see it as induction followed by deduction, or you can see it as some form of analogy. So what's the general property of this approach? The interesting thing about this approach is you see it doesn't clearly separate syntax, semantics, and pragmatics. The distinction is still there, but the processing are all kind of mixed together. Also, it doesn't depend on given grammar. It actually learns from given examples and try to generalize them to different level. But the higher the generalization goes, the weaker it becomes, unless it's supported by repeated evidence. So you see the learning process here. It doesn't follow any machine learning algorithm, but you see the learning everywhere, and it's online, one-shot, incremental, lifelong, and carried out actually by reasoning. So in ours, from the very beginning, in many publications, I have argued that learning and reasoning probably can be treated as the same thing. Okay. And also another special property is treat meaning as something that changes according to experience and context, rather than as a fixed value. Meaning can be relatively stable, but to me it's never completely fixed. So in summary, I think all domain knowledge, including linguistic knowledge, can be learned if you give it proper training. And the learning should be determined by experience. The meaning of the word should be determined by experience and context, rather than by denotation or definition. And finally, it's possible to do an NLP using kind of a general purpose learning and reasoning mechanism. That's all. Thank you.
Okay. Only one question. Okay. Yes.
To process a natural language, you need a kind of parser. And do you have a parser, or are you?
If this, currently, as I said, this is an early stage. But if this approach actually works, there's no such a thing as a parser anymore. I don't need a parser. I don't.
Okay. You won't have.
No.
Oh, okay.
No, there is no parser.
Okay. Thank you very much.